let's start with another application, right. So far we have looked at mostly the cyber security related issues, sock puppets, collusion, black markets, so on. So in this lecture we will focus on a very hot topic, right, how to model the COVID-19 pandemic spread. Okay. So last 2.5 years, I mean, I really do not need to motivate you why this is an important problem statement. In fact, the pandemic is not yet over. So last 2 years, 2.5 years, we have seen many such models, thousands of such models, which basically can mimic the way COVID-19 spreads. Now, COVID-19 pandemic is not similar to the one that we have discussed so far. For example, Ebola spread, for example, right? So, but nevertheless, people actually started with existing methods to see whether those methods are really useful for COVID-19, and then people basically improvised their models in different ways. Okay. So a quick recap of what we have discussed in the diffusion cascade chapter. We have discussed SIR model, susceptible infected recovery model, where with probability beta, susceptible population moved to infected populations, right, and this is called the birth rate of the virus, whereas with some probability gamma, an infected people and an infected person actually moves to the recovery state, right. So and if after recovery, if there is no further chance of getting infected again, so that the process ends here. In some cases, we have seen that even after recovery, say think of a normal cold, right, cold and cough like symptom, where even after recovery there is you may end up being a susceptible user, right. So there are two important parameters, beta and gamma. In fact, we also have seen the way we write the differential equation. The rate of change of susceptible user is minus beta Si, where beta is the birth rate. Now, every infected user infects a susceptible user with probability beta, right. So every susceptible user will be infected, right, with this one b into I, where I is the fraction of infected users, and since there are s number of susceptible s fraction of susceptible users, this would be the rate of change of susceptible user population, and this is negative. Why? Because the population decreases with the same amount, right. The same amount will increase, the same amount contribute to the increase of the infected user, right, and this is plus. But here with certain probability gamma, infected users again move to recovery state, therefore this is minus, and the same amount contributes to the rate of change of recovery user. Okay. And we have seen this kind of curves in the previous lectures. In fact, we have also seen a bit simpler model, which was SIS model, susceptible infected susceptible, the cold one that I mentioned, viral flu or cold one, right. From susceptible you can move to infected with certain probability alpha, and from infected you can further move to susceptible with some probability. Okay. So the model that I am going to discuss here, this is one of the lot of models that have been proposed so far, right, and this model was named as SIDARTHE. Okay. So there are these names are corresponding to different states. You have S, which is susceptible, you have I, which is infected, then there is D, which is diagnosis, right, then A, which is ailing, R, which is recognized. I will discuss all these states. T, which is threatened, right? H, which is healed, then E, which is extinct. Okay. So, susceptible population is basically the population which are prone, right, prone to this virus infection, which can which are vulnerable in that sense. Infected populations are those which are asymptomatic but infected, asymptomatic infected but undetected, the dangerous population, undetected but asymptomatic infected. D, diagnosed, asymptomatic infected but detected. Those are safe populations, because since they are detected, the other susceptible populations would basically try to avoid those populations. Then we have A, which is ailing, symptomatic infected undetected, right, they have symptoms, right, but undetected so far. And then we have recognized, symptomatic infected detected, right. Then we have T state, which is threatened, right. So these kind of populations basically suffer from major COVID problems, and it may lead to even death, right. So, from threatened state we can move to extinct. Extinct means end of life, and we also have population which is healed, H, right. So, lots of parameters, lots of states, lots of parameters. So, from susceptible state we can move to infected state, right. We have different probabilities. We have alpha, beta and gamma, right. Alpha is the infected probability, beta is the diagnosed probability, ailing is the illness probability, and delta is the recognized probability, right. With all these 4 probabilities, susceptible populations would decrease, right. You see here alpha is greater than all the other parameters. Why? Because alpha corresponds to the infected probability. So, infected state is a state which is the most dangerous, as I mentioned, because here patients are asymptomatic, they are undetected. So, with high probability they would infect others, they would basically attract susceptible population to infected population. And then diagnosed and ailing, these 2 probabilities are the least, because if and also recognized, because if things have already been recognized, already been diagnosed, identified, then people will basically avoid those populations, right. Therefore, it is less, right. We have few other parameters. We have with epsilon, so this epsilon, theta, these are also connected to detection, right. So, this epsilon basically says that this epsilon governs the detection of asymptomatic infected individuals. This is basically transition from infected to diagnosed, this one, right. Similarly, we have theta, which basically moves population from ailing to recognized, right. Symptomatic undetected to symptomatic detected. So, you see here you may want to give more weightage to theta, right, because since this is symptomatic, so there is very high chance that this would be detected, whereas in case of this one epsilon, since it is asymptomatic, there is very high chance that this would be detected. There is very less chance compared to theta that it will be detected. Therefore, you want to give more weightage to theta than epsilon. Okay. Then we have two other parameters, right. So from asymptomatic individuals, right, asymptomatic individuals can transit to symptomatic stage, right. So you see here in this figure, right, this one and this one, right, asymptomatic to symptomatic, infected to ailing and diagnosed to recognized, right. You may again want to control the parameters depending upon the actual real values. Individuals grow life threatening symptoms irrespective of the detection of their infection. We have two parameters, one is this one, right, another is this one. From illness, from ailing you can move to life threatening stage, from recognized also you can move to the life threatening stage, right. Okay. Then from life threatening stage you can move to death stage with certain probability tau, right. And then from all the states, infected, ailing, life threatening, right, diagnosed, you can directly go to the healed stage, and that is the good news, right. So with certain probabilities you can actually move to the healed stage. So these are, as you see, are lots of parameters, right, and we will use the same kind of differential equations that we use for SIR, SIS models. Again, I am not going into details, it is very straightforward. You can easily look at it by by keeping track of the state changes, and you see that rate of change of susceptible user, right, rate of change of infected user, death, ailing, right, recovered and threatening, healed and extinct, right. So if you check these parameters, I mean if you solve this differential equations, integrate it over times, you can basically draw curves T and then you change of S, change of I, right, change of D and so on. So what you can do, you can take time T, so 0 to T for tuning your parameters, right, and from T to delta T you can predict, okay, the rate of change of these populations. In fact, as I mentioned, there are many other models that have been proposed. For example, this model Gatto et al. 2020. So they use this ACIR model we discussed earlier, right, but they incorporated some sort of spatial characteristics, meaning the geographical locations, right, the other the other properties of this geography and so on, so the population density and so on and so forth. Then there was another model which was basically ACIRU model, right, which took into consideration the latency period. Okay. In fact, there was another model which considered the herd immunity, the one that we mentioned earlier, the sealed immunity, right, and that concept was incorporated into the SIR model for better prediction of the growth of the infectious people and recovered people. So I am not going into the details of this literature. This again takes a whole semester long course if I start speaking about COVID-19 spread, but you see how simple ideas of network science are useful to in fact model the deadly COVID-19 virus. Okay. So, that is about the modeling the spread of COVID-19. The next lecture we will discuss another application, which is the recommendation system, and I will basically tell you how bipartite network communities, some sort of deep learning for graphs model that we discussed in the last lecture will be useful for better recommendation of products, right, movies to users, right, and to a generic general public, right, in a broader sense. Okay. With this we stop here and we will meet next day. Thanks.